On page 718, we're going to talk about tangents. Now, it's the same word as we had with trigonometry, completely unrelated meaning, okay? Has nothing to do with sine, cosine, tangent. Not that tangent at all. So we're going to learn some properties of tangents, and we're going to use those properties to solve problems. So we need to know what a tangent is, don't we? On page 718, we have our definition. A tangent is a line in the same plane as a circle that intersects the circle in exactly one point. And that one point is called the point of tangency. Okay? So if you look at the figure here, line AB is a tangent line because it intersects circle C in one point and one point only. And the point where it intersects is point A. Point A is called the point of tangency. Now, we can also have tangent segments, but we've got to be careful with those. For instance, that only intersects the circle in one point. It's not considered to be a tangent segment, though, because if you drew it out, it would hit the circle again over here, wouldn't it? So, there are such things as tangent segments, but tangent segments are part of tangent lines. So, the black segment I have here is not a tangent segment because it's not part of a tangent line. Segment AB is a tangent segment because it intersects the circle just once, and it is part of a tangent line. See the difference? Okay. Now, if one line is tangent to two circles, it's called a common tangent. And that really happens one of two ways. Down here on the bottom left, line L is tangent to circle F and circle G. It's a common tangent for those two circles. And then look at the figure on the bottom right here. Circle F and circle G are actually tangent to each other to start with, aren't they? There's one point in here somewhere that they share in common. And then line L goes through that point and no other points on either circle. So L would be the common tangent for those two as well. Questions? All right, let's see. Let's do number one from your assignment. This is from page 721. Copy the figure shown. Y'all don't need to copy this. And draw the common tangents. If no common tangent exists, state no common tangent. So let's see. If I draw a line tangent to that circle, to the little circle, oh, it hits the big circle twice. I draw one tangent to the big circle, misses the little circle completely. Oops, I didn't mean for that to come in two. Am I ever going to be able to do this? No. No common tangent. All right, not so bad. Now, we still don't really know properties of tangents, though, do we? We just know what one is. So let's learn a property of tangents. The shortest distance from a tangent to the center of a circle is the radius drawn to the point of tangency. That fact leads us to this theorem. This theorem says a line is tangent to a circle if and only if it is perpendicular to a radius drawn to the point of tangency. So, a line is tangent to a circle if it's perpendicular to the radius at the point of tangency. So look, if I've got the radius here that's perpendicular to this line, and it's got to meet the line, though, at the end point of the radius. Can't meet the line somewhere within the radius. If it intersects the line at the end point of the radius, and the radius is perpendicular to it, that's enough to prove that line L is a tangent. You follow me? And then vice versa. If you know already that line L is a tangent, when you draw it and you draw a radius to it, the radius must be perpendicular. So, If you see that the radius is perpendicular to a line, it's a tangent line. If you see a line's a tangent line and a radius intersects it, the radius is perpendicular to it. Now, all of this, though, you got to remember, it's got to intersect at a point on the circle. This is no good if you draw a line L through there, is it? All right, it's got to intersect at the end point of the radius, at a point on the circle. As long as that's what happens, whenever the radius is perpendicular to the line, it's a tangent line. Whenever it's a tangent line, the radius will be perpendicular to it. Okay? That's two theorems in one. All right, let's see how this works out. So let's do a few more from your assignment. It says determine whether segment FG is tangent to circle E and justify your answer. So look what we have here. We have segment FG, and we want to know whether or not it's tangent. Well, according to our theorem, for it to be a tangent line, what has to be true when that radius intersects it? It's got to be perpendicular, doesn't it? How are we going to decide whether or not that's a right angle? Pythagorean theorem. Look at the red triangle I just outlined. If that's a right angle, then we can find it, or we can prove that it is, by doing this, can't we? So, if c squared equals a squared plus b squared, that's a right angle, the radius is perpendicular to the line, that proves it's a tangent line. If c squared does not equal a squared plus b squared, then it's not a right angle, it's not perpendicular, the radius is not perpendicular to the tangent, or to the line, it's not a tangent. Make sense? You follow me on this? All right. If that's a right triangle, which of those lengths must be the hypotenuse? The 12. So 12 squared, and then on the other side, 6 squared plus 10 squared. 12 squared, what's that, 144? And then that'd be 36 plus 100. All right, not a right angle. So the radius is not perpendicular to that line. That line's not a tangent line. So segment FG is not tangent to circle E. Now, to justify your answer, we already did that, didn't we? The work we show up here is justifying our answer. So you show your work, you've justified your answer. Everybody understand how that works? Let's try another one, just on the safe side. Number 3. Now, number 3, they're tricking us here a little bit. We got to be careful because I want to do the same thing, right? I want to say, okay, there's the radius. There's the segment that they're asking me whether or not it's tangent. I want to see whether or not that's a right angle. So I'll do the exact same thing I did in number 2. I'll complete that with the hypotenuse, and then I'll do c squared, a squared plus b squared. So no tricks so far, everything's fine. Here's where you need to be careful. It's not a trick. It's just you need to be careful. What's the length of that potential hypotenuse? Can't be 24, can it? Okay? So look, that length of 24 is not the length from F to E. 24 is the length from F to the circle. Okay? If they wanted it to be from F all the way to E, they would have done this. See where they did the little measurement marks? Okay? So, if from F to the circle is 24, what's the distance from the circle to E? 15. Because if that radius is 15, they're all 15, which means 39 is the length from F to E. Everybody follow me on that? So again, it's kind of tricky, but it's not a trick. I expect you to be able to notice that and figure that out. Okay? So, let's see then. 39 would be the potential hypotenuse, so 39 squared. Then we'd have 15 squared plus 36 squared. And let's use our calculator. 39 squared is 1521. Then I can do this in one step. 15 squared plus 36 squared. Oh, that's also 1521. So that is a right triangle, which means angle G is a right angle, which means the radius is perpendicular to the line, which means it's a tangent. All right, so what do we answer? Segment FG is tangent to circle E. And to justify your answer, we just did. That's what's in purple. All right, so you think you got those? All right, now, similar concept, different question. It's actually a question over the same theorem. This time, they're not asking us whether or not a segment's tangent. They're telling us. Assume that segments that appear to be tangent are tangent. So segment MN appears to be tangent, so our directions tell us it is. We're supposed to find x. So this time, instead of finding out if we have a tangent line, we know that we do. Let's use it. And we're really using the same idea, because since that's a tangent line, it's perpendicular to the radius, isn't it? Well, can't we do the Pythagorean theorem to find x? Yeah, we can. Okay, so one leg squared plus the other leg squared equals the hypotenuse squared. Just make sure you call the right one. The hypotenuse is the segment opposite the right angle. Well, let's see. That'd be what, 144 plus, what's that, 256 equals x squared, so that's 400 equals x squared. What's the square root of 400? 20. Sorry, 20. All right, not too bad. You thought the Pythagorean theorem was going to go away someday, didn't you? It's not. It's not going to go away. All right, number 5. Again, assume that any segment that looks like it's tangent is tangent. So segment BC is tangent. That means it's perpendicular to the radius. We can use the Pythagorean theorem again. So one leg squared, x squared, plus the other leg squared, 30 squared, equals, 18 is not the hypotenuse. What's the hypotenuse? X plus 18, good. Because if one of the radii is x, so is the other one. So the whole distance from A out to C has to be x plus 18, doesn't it? And we have to solve for x. So when I square the hypotenuse, it's that parentheses, x plus 18 squared. Now, before we do that, it turns out to be easier than you're afraid it's going to be. You guys with me on setting this up? All right, we know what x squared is. It's x squared. 30 squared, 900. Now, to square something, you multiply it times itself. So to square x plus 18, I multiply x plus 18 times x plus 18, FOIL method. X times x, x times 18, 18 times x, 18 times 18. What is 18 times 18? 324, is that what y'all was telling me? So, when I combine like terms, I get x squared plus 36x plus 324, don't I? because 18x plus 18x is 36x. So, it appears we have a quadratic equation, but we don't, because look what happens. If I subtract x squared from both sides, I'm left with 900 on one side, and I'm left with 36x plus 324 on the other side. Well, I'm good with that. That we can do. Everybody with me? So what's 900 minus 324? 576. And then what's 576 divided by 36? 16. So again, as in so many times when we've been working this, look, the algebra, they can make that as difficult as they want to make it, can't they? We've got to learn the geometry. So the whole point of these last 4 examples, if you know a line's tangent, then it's perpendicular to the radius. If you see a line that's perpendicular to the radius, but not within the circle, through the circle, it just barely touches it, then it's a tangent line. All right? Okay. Another property of tangents is this. If 2 segments from the same exterior point are tangent to a circle, then those 2 segments are congruent. So in this example, I draw segment BA, it's tangent to the circle. Segment BC, it's tangent to the same circle. Those 2 segments are congruent. And I got to say segments, I can't say lines, can I? Lines aren't congruent. Segments are. So those 2 segments are congruent. So if the length of AB was 10, what's the length of BC? 10. Let's see how that works out. Number 6. Again, if the segment looks tangent, it is. We're supposed to find x. Well, these 2 segments are from the same exterior point, aren't they? So they're congruent. So 5x minus 8 equals 3x. Questions? Okay. So negative 8 equals negative 2x, and 4 equals x. And again, they could make the algebra hard if they want to. But get the concept down. Now, we're going to use that same concept on number 7. It says a landscape architect is paving the 2 walking paths that are tangent to 2 approximately circular ponds as shown. Since the ponds are approximately circular, are we going to get exact, take it to the bank kind of answers? No, I mean, we may get whole numbers, but there's going to be approximate whole numbers, aren't they? Okay? So the lengths are given in feet. We're supposed to find the values of x and y, and then answer the question, what is the total length of the walking paths? All right. Well, look here. From this exterior point, I have this tangent segment and this tangent segment to the same circle. So don't those 2 tangent segments have to be each other? This will give us a way to solve for x. So x plus 250 has to equal 4x minus 500. Let's subtract x from both sides. We'll get 250 equals 3x minus 500. Add 500 to both sides. We'll get 750 equals 3x. So x equals 250. All right, so we've answered one question. Now, let's start working on finding y. Well, look here, do some thinking with me. All right, watch what I'm doing here to the figure. Those 2 red segments are congruent, correct? If I go from the same exterior point again to that tangency, and then to that point of tangency, aren't those 2 black segments also congruent? if the two black segments are congruent and the two red segments are congruent, don't these two blue segments have to be congruent? Segment addition possible. I mean, convoluted version of segment addition possible. So look, finding y is actually easy. Since we know that x is 250, I'll make that 250 plus 25, that's 275. So if that blue segment's 275, the other blue segment's 275, and guess what y equals? 275. Now, could I have set the length of the black segment equal to the length of the other black segment? Sure. But I think this was a little faster. I know it's a little faster. Make sense? Last question. What is the total length of the walking path? Well, look, let's do the top one, the one that goes above the ponds. If x is 250, so 250 plus 250, so from here to here is 500. And then from here to here is 275. So that's 775 for one of them. There's two of them. So the total distance is going to be 775 plus 775, which is 1550, 1,550 feet. Questions? All right. One more property. One more concept. A polygon is circumscribed about a circle if every side of the polygon is tangent to the circle. Previously, we had circles circumscribed about polygons. And for that to happen, each vertex of the polygon had to be a point on the circle. Now we're doing it the other way around. The polygon is circumscribed about the circle. So the circle's on the inside. For it to be circumscribed, each side of the polygon is tangent to the circle. Look at this triangle they have here on the screen. That side's tangent to the circle. So is that side. So is that side. For that quadrilateral next to it, each side is tangent to the circle. For the hexagon next to it, each side is tangent to the circle. But look at the ones that aren't. First, figure 1 here. I don't even know what they're, obviously not. They are intersecting each other. Okay? Not circumscribed. But number 2 could fool you because that side's tangent to the circle, so is that side, but the fourth side's not. So not circumscribed. And then the other one, if all you remember is, oh, a polygon circumscribed means that the circle's on the inside, then you might fall for it for this third figure. But none of those sides are tangent to the circle. Okay? Now, how's this useful? Well, actually, believe it or not, it's pretty useful. For number 8, triangle JKL is circumscribed about circle R. Find X, then find the perimeter of the triangle. Okay. Now, there's something real neat here. Since each side is tangent to the circle, that means, let's concentrate on point L. See point L? Point L is an exterior point. LN is a tangent segment. LO is a tangent segment. Since they're tangents from the same exterior point, those two segments are congruent to each other. Okay? So that means that x plus 3 equals 4x minus 9. And then we solve for x. So that'd be 3 equals 3x minus 9, 12 equals 3x, and 4 equals x. So the answer to A is 4. Now, to get the perimeter, we need to know the length of each side. Believe it or not difficult to get. Because look, now that we know x is 4, 4 plus 3 is 7, so the length from N to L is 7. So the length from L to O is also 7, right? Now, Watch the magic. Look up here at point K. KM is a tangent segment. Its length is 7. KN is a tangent segment from the same exterior point. What's its length? The same, 7. JO is a tangent segment. JM is a tangent segment from the same exterior point. If the length of JO is 12, what's the length of JM? 12. Well, now it's easy to get the diameter. Okay, I have two sides. Well, what's 12 plus 7? All right, so I've got a side of 19, and then down here, JL is also 19, and then KL is 14, 52. And I tell you, a lot of times, I don't even bother actually finding the length of the sides. I'll just add up the little pieces. 7 plus 7 plus 7 plus 7 plus 12 plus 12. Because in my head, I can do 7 times 4 pretty quickly. I can do 12 times 2 pretty quickly. But, you know, whatever works best for you. All right. Questions? Your assignment then from this section is page 721, 1 through 27, 35, 38, and 40 through 43.